So this is Chapter 8, Section 3, Separation of Variables. So looking back into the past, we learned the derivative. But within that derivative, we learned that the letter on top is your function, and the letter on top is your variable. And since in this case, these are our variables, the antiderivative is pretty straightforward. Use the power rule, x cubed over 3, x squared over 2 plus c. That is because these are your variables and they match up. Same thing here. X is your variable. That's your variable. So we want to find the derivative of what is sine, and we would say minus cosine x plus c. And the derivative of that should match with what we have. So we're finding solutions. These are called solutions. So we're getting y equals, or we're finding the function y, where if we take the derivative, it equals what we have. And so here, we want the solution of this. It would be ln absolute value of x plus c. The derivative of that is 1 over x. So these are all things that we have done the first semester. And I will do this one for you. X cubed over 3, x squared over 2 plus c. It all works nicely because our variable is x, and these are all x's. Now, if you notice these next two, we have a problem. The y is a problem because we can see that our variable is x. And although we do have an x here, we also have y, we have the function. We've never had a situation where the function has actually appeared in our derivative. When that happens, that's when we have to use separation of variables. And you can't always use separation of variables. It doesn't always work, but it's something, a technique that you're going to have available to you that you can try to do. And so that's the key. You need to recognize when you might have to use separation of variables, and that's going to happen when your function, y, or whatever that function is, appears in your derivative. So the steps you're going to take, you're going to separate the variables. Anything with an x, you're going to move to one side, and anything with a y, you're going to move to the other. Then once you do that, you're just going to find the antiderivative of each side individually. That's going to bring a constant in. You always get a constant. Then you're going to solve for that constant. And then to get the solution, you're going to isolate your function. You can get y equals. And so that's going to be the function, which will be the solution to the differential equation. So we're going to do an example here. We have dy dx equals x over y, and we immediately see that our function y appears in our derivative, and that's a hint we're going to have to separate variables. So if I multiply both sides by y and multiply both sides by dx, you should see that I can manipulate to that. I have moved everything with a y on one side, everything with the x on the other. That's called separating your variables, and on the AP test, on the multiple choice, you'll get a point for doing that. Step 2. Now what's interesting, if you look at this, when we integrated, you were told, hold on here, that this tells you what your variable is. So our variable is x. By separating our variables, when we integrate, this is telling us our variable is y, and so now that y becomes our variable and not our function because the way we separated it, and so things work out nicely. I get y squared over 2 plus c, x squared over 2 plus c. Those c's are different, so I'm going to label them c1 and c2. Okay? But now I'm going to subtract c1 from both sides, and I'm going to end up with this. So I subtract that from here, I end up with that. But notice c2 is just a constant. c1 is a constant, and a constant minus a constant is a new constant. So what I'm going to do, I'm going to replace c2 minus c1 with c, where c is equal to c2 minus c1. But again, this is just a constant, and c2 minus c1 is a constant, so it's the same thing. All this to say, all of this work here is not necessary. You don't need that. When you separate variables, you only end up with a c on one side. So we could ignore all that stuff before, okay? So we can eliminate all of this. And go right to just having a single c. All right, so now remember from doing slope fields, for this differential equation here, this is the slope field. And depending on where you start, remember you have different solutions. So this slope field represents all the different solutions, all the different functions, where if you plug it in here and here, you would have a true equation. So this, depending on the c, will give you different functions. So once they give us a point, -1, 3, let me go ahead and put a dot there. That's going to tie us to a specific solution. Okay? Now we want the equation of this specific line. So to do that, you have to find what c is. So let's go ahead and do that. So we know it goes through -1, 3, where that's x and that's y. So off to the side, in my equation, I replace y with 3, x with -1, and again, just the 3 goes in here, and then -1 goes here, and we get 9/3 equals, wait a second, 9/2. That's not a 3, that's a half. Equals 1/2 plus c, subtract 1/2 from both sides. And so c comes out to be 4. So that is the c placed into this equation that gives us that particular solution. So what do we have here? Now, the last step. So I've done the first step. I separated my variables. Then I integrated both. Step 3, I solve for c using a given point. So now you put that c in for c. Now you have the particular solution. So this is the equation that matches up with that graph. So now I have to solve for y because I want y equals. When I solve a differential equation, I want to find the original function. So I'm going to multiply both sides by 2. Distributing that, I get y squared, x squared plus 8. And we run into a little snag. When we square root both sides, we get a plus or minus in front. Now, here's the problem. Actually, I just realized I put the wrong point in, but oh well. It's not what I wanted, but it will have to do. Okay, so do I do plus or minus? Because both of those will work. But look at the graph where it's located. Your graph is here. Y is positive there. When you plug in -1, you want to get a positive y. You want your y's are always positive, so you're not going to use a negative. So you would actually not use that. Your solution in this case is just a positive value. Now, I meant to actually give you a -3 here. And that would have forced you to choose the -1, not the positive one. But all is well. So there we go. So that's separation of variables. I'm going to run through a few examples of these that have appeared on past AP tests. And pretty much you know what you need to know. Now it's just practice And a lot of it's algebra skills and trig skills. This appeared in 2010. And so if you took the AP test in 2010, there's a good chance you would have had this FRQ. So what do they give you? They give you a differential equation here. And they are nice and they give you the second derivative. And then they tell you f of x is a particular solution to the differential equation. So that function is one of many solutions, but it's the one specifically that goes through 1, 2. Meaning, if you put f of x in for that y and in for that y, this would be a true equation. So that's what it means to be the solution. So part A, it says write the equation of the line tangent to the graph at 1. Well, we know f at 1 is 2, so really it's at the point 1, 2. And so when you see equation of the tangent line, you should immediately go to the equation of a line in point slope form. We know x1, y1, that was given as 1, 2. Now all we have left is the slope of the tangent line. What gives you the slope of the tangent line? The derivative, right? So the slope is the derivative evaluated at a specific point, 1, 2. And so we're going to plug in 1 for x, 2 for y, and we get 8. So the slope is 8, and I'm going to do some fancy schmancy algebra and solve for y. Here is my tangent line equation. And they want me, in part B, let's do that next, we did part A, use the tangent line equation for part A to approximate f at 1.1. F at 1.1 is going to be approximated by our tangent line at 1.1, which is 8 times 1.1 minus 6. There's my answer for my tangent line approximation. Okay, let's keep reading though. Given that f of x is positive, so they're telling us that the function is positive on the interval from 1 to 1.1. Is the approximation greater or less than 1.1? So this is a justification that we learned during the first semester, and it has to do with the concavity, so I'll give you just kind of a visual. If your function's concave down and you draw a tangent line, clearly the approximation of the tangent line, that's bigger than the actual value. So it has to do with concavity. If you have something that's concave down and you draw a tangent line, now it should be obvious that all points on the tangent line are less than the actual value. So you're going to look at concavity. And concavity has to be on the interval from the point of tangency all the way to the point being estimated. Okay? Well, our point of tangency is 1. Our point being estimated is 1.1. So we need to show the second derivative is either positive or negative on that interval. So let's evaluate. We have the second derivative given right here. So we're going to find the second derivative. We're not going to find it. They gave it to us. Now here's our observation. Since y is always positive, how do we know that? Because they told us the function's always positive, so the y value is always positive, and 1 plus 3x squared y squared is always positive, right? Because when you square something, it comes out positive, and you add positive to it, it's going to always be positive. Therefore, the second derivative is going to be positive for all values, for all points. Okay? So if it's always positive, that means it's concave up. That means we're going to have a under, all right? So the question asked us, is the tangent line equation, okay, is the approximation greater or less than the actual value? So is our approximation too big or too small? And since we've concluded it's concave up, our approximation is going to be too small, so we need to state that with justification. You have to give a reason. You can't just say it's smaller because I said so. It's smaller because it's quite obvious. Those are not acceptable answers. You have to actually give an justification based upon things we have learned in this class. Okay, so how are we going to do that? Well, let's do it here. We're going to say the tangent line the tangent line approximation from part B is, and they ask specifically greater or less than, we are concave up, is less than, I don't know how to write, is less, is less than the actual value. And there's other ways to write this. Because the second derivative is positive, bam. That's the reason. Second derivative is positive, therefore any tangent line will be an under approximation. That was part C. So you had to show that the second derivative is always positive and write a conclusion. Well, that's part B. Sorry, that was part B. Part C, find the particular solution that goes to the point 1, 2. So we're starting with our differential equation. I should have room here. xy cubed. Oh, times y cubed. Okay. So part C, they're asking for the solution to this differential equation. And they don't say use separation variables. You got to recognize that. And how do you recognize that? The way you recognize that is to see our function is y. And in our solution or our derivative, we have y. Whenever your function appears in your derivative, you need to separate variables. So step 1, divide both sides by y cubed and multiply both sides by dx. So you would actually get a point on the AP test for separating these variables to look like that. First step. Step 2 is you would integrate both sides. So I'm going to rewrite this. This is going to be dy. Actually, I'm going to move that y to the top. Y to the negative 3 dy equals integral x dx. Now it's easy. I add 1 to the exponent and divide by that. I add 1 to the exponent and divide by that, and I get a plus c. So believe it or not, back in 2010, you got 1 point for these antiderivatives. You actually got a point for just writing plus c. Just for writing that, you actually get a point. Kind of ridiculous, but that's what they did back then. Okay, our next step is we got to calculate c. But before I do that, I want to make this a little nicer. Okay, so we know, or we are told, it goes to the point 1, 2. So I'm going to click 1, 2 into this and solve for c. So I'm going to get negative 1, 2 times, and it's y is 2, equals 1 squared over 2 plus c. So that's going to be negative 1/8 equals 1/2 plus c. I'm going to subtract 1/2. That's going to give me negative 5/8 if you do your arithmetic right. And so now I have found c. You would get a point for finding c. Okay? And we're almost done. Now I just need to stick that back in to get a particular solution. So I'm going to plug it in here. So we'll do that next. I'll get negative 1 over 2y squared equals x squared over 2 minus 5/8. Now there's a few ways you can solve for y. My desire is to flip this upside down to get the y on top because I'm trying to solve for y. But I can't flip this unless I rewrite that with a common denominator. So this will be 4 with the 4 there. Now we get 4x squared minus 5 over 8 because we got a common denominator. I'm going to take the reciprocal of both sides. So I'm going to flip this side. I'm going to get 2y squared negative. If I flip the other side, I'm going to get 8 over 4x squared minus 5. I'm now going to divide both sides by negative 2. Now, if I divide by negative 2, I multiply by the reciprocal, which is negative 1/2. So the 2 ends up on the bottom. Convince yourself of that. And then just to tidy it up, I'm going to cancel those out and leave a negative 4. And then I square root both sides. Okay. Now, we could deal with that negative 4 a couple different ways. But we need to square root. Don't forget the plus or minus. Now, that answer should be fine in that form, but let's double check. When I plug in 1 for x, it needs to equal 2. If I plug in 1 for x, right, I get 4 minus 5 is negative 1. Negative 4 divided by negative 1 is positive 4. Square root of positive 4 is 2. That's what I'm supposed to get, but I'm supposed to get a positive 2. So therefore, I don't need the negative, okay, because the answer has to come out positive. So that's my answer. Now, if you want to simplify, a couple things. You don't have to. That's pretty much done. I'm going to move the negative to the bottom. And when I do that, the 5 becomes positive and the 4x squared becomes negative. And the square root of 4 is 2, so I can do that. And I'm just going to get it to the form that is in the solutions. Actually, they went even... No, I think they stopped right there. And so that's the answer to that problem, 2010. All right. This one, the next one we're looking at is 2014. So they give you a differential equation. And this one's going to be a little crazy, so kind of hang in here. Pay attention. This one is a lot of pre-calculus stuff or algebra 2 stuff. So you have a differential equation. You have f of x is a particular solution with the initial condition 0, 1. So if you go to the point 0, 1 and draw that solution, that's what f of x is. So in part A, the portion of slope field differential equation below, okay, you want to draw the solution that goes through 0, 1. So 0, 1 is right there. And you just have to draw the curve, and you have to follow these slopes and make sure that your graph is parallel to all those. Doesn't have to be perfect, but it should be pretty close to that, okay? Like I said, doesn't have to be perfect. It just needs to be pretty close. Okay, so now we are going to move to part B. So that's part A. Let's see. That one, I'll tell you how much that was worth for doing that. Probably 1 point, I would guess. See what they gave me. Yeah, 1 point for drawing that solution curve. Okay, they actually went a little lower on their graph. I think they actually came a little bit lower when they drew theirs. Okay, but I think we're close enough. Part B. Write the equation of the tangent line to the solution curve and use this equation to approximate f at point 2. So part B, I'm going to do right here. A quick tangent line again, okay? You should immediately do that. Now, do we know the point of tangency? They tell us 0, 1, so we're going to plug those in here. But the slope, how do you find the slope? The slope is the derivative at that point. So somewhere you have to show the work that you evaluated the derivative at the point of tangency, which was 0, 1, and find that. That's going to be 3 minus 1 times cosine 0, which is 2. So we found the slope, plug it in here. There is your tangent line equation, right? Then it asks you to approximate f at point 2. So the actual blue equation at point 2, I don't know that equation, so I use my tangent line to approximate it at point 2. And that's going to be, you know what, let me solve this for y. Y is going to be 2x plus 1. There's my tangent line approximation. So I'm going to plug in 0.2 into that. So it's 2 times 0.2 plus 1. There's my answer. I mean, if you wrote that as 1.4, you'll be fine. But if you make a mistake, you're going to lose that point. That's worth 1 point. You don't want to lose that. All right. So here is our craziness. Here's where you want to really focus. A lot of stuff's going on, a lot of work here that's happening. So part C, find the particular solution going through 0, 1. We want to solve for y. Now, we take our differential equation, and hopefully, when you look at that and you say, man, I need to integrate this to solve, you're going to notice your function's y, and you have a y in your derivative. You need to separate variables. I'm going to divide both sides by 3 minus y and multiply both sides by dx. Now you notice all your x's are together, your y's together. They give you a point for separating those variables in this particular year. Next, you recognize I have to integrate both sides. The right side's pretty easy. That's just sine x plus c. The left side is a little tricky. You have to do a u sub. So we have to let u equal, oh wow, I need some room here. I'm going to scoot all this over here because I scrunched myself over way too tight. So let me move it over. Okay. I'm going to let u equal 3 minus y. That makes du minus dy. Now, do I have a minus dy here? I don't, but now I do. And so I can rewrite this as the integral with a negative. The top becomes du, the bottom becomes u. And that, you should know, is ln, absolute value u. So on this particular error, they actually gave you a point. Oh, we got to sub u back in. U is 3 minus y. So in this particular year, they actually gave you 1 point for that, 1 point for that, and 1 point just for writing plus c. Now, in recent tests, they don't do that. They don't give you a point for the plus c. They give you a point for finding c. So we're going to find c. So we know we go through 0, 1 because they told us here. So we're going to plug in 0 for x and 1 for y. Well, this is pretty easy. This is ln 2. Sine of 0 is 0 plus c. So c is minus ln 2. They actually gave you a point for finding the c. Now we're going to put that c into our function here. So therefore, we're going to get opposite ln 3 minus y equals sine x plus c. Now, if we had the slope field for, oh, we do have the slope field for this. There is one particular solution that goes through 0, 1. It's this blue line. We are trying to find the equation of that blue line, but we got to plug in c, and I didn't plug it in there. C is minus ln 2. So there is our equation, but now I have to solve for y. All right, solving for y is 1 point, but here we go. Here we go. I'm going to have to do some fancy schmancy work here. And actually, this one's not too bad. Now that I look at it, it's not too bad. So I'm going to multiply everything by negative to get rid of that negative, okay? So I'm going to get ln absolute 3 minus y equals, it's going to be opposite sine x plus ln 2 because I multiplied by negative, so these switch signs. Now, I want to get rid of ln, so I have to e both sides, okay? So e to that power and e to that power. Well, the e and ln are inverse functions. They're going to cancel out, leaving 3 minus y. And I'm going to get e to the minus sine x. And I'm going to do something weird here. And you got to be okay with it. So there's a rule for exponents that you learned once upon a time. And that rule was, if you have two exponents with the same base, you just add the exponents. Well, minus sine x plus ln 2 gets you that. So I just went backwards. These were being added. I broke it up into two separate ones. And here the e and the ln cancel, leaving just a 2. So I get 2e to the minus sine x. All right? We're still not done. What do I do with the absolute value signs? Okay. I'm going to do something that hopefully makes sense to you. So this could be positive or negative, and it wouldn't matter because the absolute value makes it positive. So this could be positive or negative, and it has to equal that, right? So if I get rid of the absolute value sign, I would get plus or minus 2e to the minus sine x, right? Because if this were equal to a positive of that, the absolute value would make it equal to that. And if I had the negative, the absolute value of that would get rid of the negative, I'll equal that. So that's the equivalent. When I get rid of the absolute value, I put a plus or minus there. Now I'm going to solve for y. So y is going to equal 3 plus or minus 2e to the minus sine x. What just happened? Okay, I add y to the other side. So I get y by itself. I have 3 out by itself. I need to add and subtract this to get it over here, so I end up with that. But here's the problem. I can't have two of these. There is one particular solution. It's this one. I need the one that gets me 0, 1. So either the plus or minus is going to get me 1. So if I plug in 0 here, sine of 0 is 0, e to the 0 is 1. So all this is 1 when x is 0. And I want to get what for y? I want my y to be 1, right? How do I get 1? 3 plus 2 or 3 minus 2? It's going to be 3 minus 2. So therefore it becomes 3 minus 2e to the minus sine x. There is your answer. And I'm done. So you have to make sure that you pick the right plus or minus to get the particular solution that we're looking for. All right, I have 2 more to go. This is the killer problem. This is the one where most AB students just bombed badly, okay? And it was just a separation of variables stated in a way that confused students badly. And I'll show you why. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. So I need to write that down. I highly, highly, highly recommend you annotate these things. So in 2010, the amount of waste is 1,400 tons. W is the amount of waste, so W equals 1,400 tons. I'm boxing this. You shouldn't box it. I'm just highlighting things. Then they tell us that the increasing function W models the total amount of solid waste stored in the landfill. So what does W represent? Write that down, W of T, or just W. And what does that represent? That represents the total amount of trash. If you read it, that's what it's saying. And W is increasing. It's important that you write that down because you might not need it, but the increasing function W, they told you it's increasing, so write down increasing. And what does W represent? The total amount of trash. Okay? It says the planners estimate that W satisfy the differential equation. So given that differential equation, I'm going to kind of copy that down. Okay? W is measured in tons. Okay, I can write that down. Tons. T is measured in years from the start of 2010. T is measured in years from the start of 2010. So in 2010, I'm going to write this down. T is 0 in 2010. Now here we go. Part A. And I'll explain why people did so poorly. In Part A, use the tangent line to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contained at the end of the first 3 months. So my variables are W and T. Instead of X and Y, I have W and T. Well, am I given a starting point? I sure am. If you read this, T is 1/4. No, liar, liar, pants on fire. The tangent line at T equals 0. You want the tangent line at T equals 0. So we know the point is going to be 0. But that's T. What's W? I need W. So this will be TW. Okay? What's W when T is 0? Well, they told us that. Look at, when T is 0, we have 1,400 tons. So that's 1,400 tons. That's our point of tangency. So we're doing the same thing, except instead of X's and Y's, we have W's and T's. We need the point of tangency to tell us when T is 0. So this is the hard part. What's W when T is 0? You have to actually kind of figure that out. But they told you that at the beginning. In 2010, we started with 1,400 tons. So I'm going to plug those into our equation. W minus 1,400 equals T minus 0. But I need the slope. Gee, what tells us the slope? The derivative. What is the derivative? They gave it to us right here. Okay? So we want the derivative to get the slope of the tangent line at T equals 0. Well, here's our equation. 1/25. Wait a second. What's W? I have T as 0. I don't know W. Again, when T is 0, W is 1,400. So this will be 1,400. Now we have our slope. It's 1/25. 1,400 minus 300, that's 1,100. 25 goes in 1144 times. How do I do that? Because 4 25s make 100. I have 11 hundreds, so I need 44. See how I did that? So 44 is the slope. Bam. Let's see. So I want to use this. So I'm going to solve for W. It's going to be 44t plus 1400. That's my tangent line. And it says, use this tangent line to approximate the amount of solid waste at the end of the first 3 months, or when t is 1/4. So the amount of waste, W, at 1/4 is approximately equal to 44 times 1/4 plus 1400. That's it. You don't have to go further than that, because if you simplify that incorrectly, you will lose the point you already had. So you shouldn't be simplifying it, but it's going to be 1,411 tons. Okay? So let's just keep going. This is 2011. We'll take a look at the next step. So it's asking, part B, find the second derivative. A lot of people were thrown off on the second derivative, and not surprisingly, I'll tell you why. Let's start with the first derivative. It's because there's little very subtle things that threw people off on this problem. So dw dt is 1/25 w minus 300. So here's what a lot of students did, I think. Oh, this is easy. There's my variable. This is wrong. Don't copy this. So it's 1/25w minus 12. And then the derivative, that's easy. Whoops, I didn't mean to do that. The derivative. So if I take the derivative again, the derivative is just 1/25, because that's 1/25 and our variable. That's not right. I'll explain why. So when you take the derivative of both sides, you get the second derivative. That's what we're trying to find. But here's my question to you. What is your function and what's your variable? And if you look, t is your variable, w is your function. This is a function, or that is a function, not a variable. You need to use chain rule on that. So the derivative would be 1/25 times the derivative of w with respect to t. T is your variable. That's dw dt. Okay? That's where a lot of students messed up. They just assumed this was my variable, so the answer is 1/25. I'm done. But it's not. W is your function, so the derivative of function is dw dt, because it's respect to time. So then they want us to use this information. Oh, they want in terms of w. So what is dw dt? I have to replace dw dt with what it equals, that. So I got to place that there. So that's going to be 1/25 w minus 300. Again, you should stop there, but some of you aren't going to be smart enough to do that, and you're going to do that. But that is your second derivative right there. Okay, so again, remember, if a graph is concave up, the tangent line will be an under approximation. If the graph is concave down, the tangent line will be an over approximation. So the approximation part A, we have to figure out if this is positive or negative. Is the second derivative positive or negative? Look at that. It depends on what W is, right? If W is greater than 300, the second derivative is positive. If it's less than 300, it's negative. But what is W? That's where you have to go back and look. W is the total amount of trash in the landfill. Well, how do I know if it's more than or less than 300? How do I know that? Then you just have to use your brain a little bit. At the beginning, we started with 1,400 tons. And you might say, well, what if the trash decomposed and we end up with less than 300? But they tell you the amount of trash is increasing. So the amount of trash is going to be greater than or equal to 1,400 tons, right? So I would say, since W is greater than or equal to 1,400, therefore the second derivative is greater than 0. It's going to be positive. So if it's concave up, our tangent line is going to be an under approximation. So to answer part B, since the second derivative is positive, therefore the approximation, wow, sorry for my horrible writing. My approximation from part A is it under, over? Concave up means is an underestimate. Bammo. Done. So that's part B. Okay? So now we're going to move on to part C. You can see probably why this was such a difficult question for so many people. So many subtle things. I'm going to erase some of this so I can do part C. Part C is a bit crazy. Should I erase more? Yeah, I'm going to erase all this. I don't need it. I don't think I need it. So part C. Find the particular solution. So we want to solve for W, right? With the initial condition of 0, 1,400. So we need to see, to solve for W, I need to integrate this, but W is our function, and there's our function. If that were t, this would be easy. T squared over 2, done, right? And that's 0. But it's not. That's our function. This is our function. So we need to separate variables. So the first step is to do that. Move the W by dividing, and then move the T to the right side. 1 point for separating the variables. Now we're ready to integrate both sides. The right side is super easy. 1 over 25 is a constant times T plus C. If you have a constant and you integrate it, it'll just be the constant times your variable. I like that. That's really easy. That's really nice. The right side, I have issues. U sub. U is the denominator. Du is dw. So this becomes, quite simply, du over u equals that. That becomes ln absolute u equals, I'll put t over 25. Now I replace u with w minus 300. All right, let's keep going. Now, there's actually a way to get rid of this absolute value right now, but I'm not going to use it. But you could. You could say, since w is always greater than or equal to 1200, like we said earlier, this is always positive, therefore I don't need the absolute value. But just to be cool, I'm not going to do that, just to show you other techniques of doing this, okay? And on top of that, normally we would find C right now. I'm just going to find C later, okay? Now you can find C at any point in this process, but I'm going to find it later. Check this out. I want to get rid of the ln, so I'm going to e both sides. Those are going to cancel nicely and leave me this. On the right side, I'm going to split those up into 2, just like I did earlier. Just to confirm, when I have something like this, if you have the same base, you add those. Well, that's what's happening here. So we just did that backwards. I'm now going to get rid of the absolute value. But if I get rid of the absolute value, I have to put a plus or minus here. And I'm just going to put e to the c first. Now, here's my wild and bold step. C is just a constant. E is just a constant. So that's just another constant. And it could be positive or negative, and the only difference is you'd have different graphs, one above the x-axis, one below the x-axis, so they represent different particular solutions. Well, I don't know which particular solution, but I'm going to do this. I'm going to let k equal plus or minus e to the c. And what's that going to do for us? Watch this. W minus 300 is equal to k e to the t over 25. That is so beautiful. I'm going to add 300 to the other side. Now, I need to figure out this constant, but I am given a point that it goes through. Remember at the very beginning, you're told it goes through 0, 1400. So I know 0, 1400 must be a solution. So I'm going to plug that in. 1400 equals 300 plus k e to the 0. Okay, I got this. E to the 0 is 1. Subtract 300 from both sides. I get 1100 is my k. So all I have to do is plug this in here, and I have my solution. And so what happened, remember we couldn't figure out, is it positive? Is it negative? I'm not sure. Well, by plugging in the initial conditions, the positive negative took care of itself. I didn't have to do it. It just took care of itself. And here is my answer for the particular solution. So that's that. And again, like I said, you could have solved for C way back here. You could have plugged in 0, 1400, found C. You would have had a number here, and everything would have worked out nicely. But the plus or minus, you'd have to double plug in that number to make sure you get the right one, and you'd get the same answer. So you can go ahead and take a look at that. I have one last example here. We're asked to draw a slope field at the 6 given points. So I need to show some work. What is the derivative at 0, negative 1? That's that point. Here are my 6 points, by the way. I just have to do those 2 points, 6 points. What's my derivative? I probably should have done it in, I don't know how to explain it. I probably should have did this on top, that in the middle, that on the bottom, but I'm reversing them. And you want dy dx at xy equal 0, 2. So what would that be? 0, negative 1. So if I put a 0 here and a negative 1 here, that'd be positive 1. So I'm going to get positive 1. And then 0, 1. If I put a 0 here and a 1 here, I'm going to get negative 1. And 0, 2. So if I put a 0 here and a 2 here, I'm going to get negative 2. And now I'm going to have to also find it. Ooh, I should give myself more. I'm doing this all crazy. Okay. Then I need to find the derivative at 3 more places. Okay, it's going to be, and I'll do it correspondingly, 1, 2, 1, 1, 1, negative 1. Okay, 1, 2. So if I put 1 here and 2 here, that's going to be 0. And then 1, 1, it's going to be 2 minus 1, it's going to be 1. And 1, negative 1, 1, it's going to be 2. Minus negative is plus, that's going to be 3. All right, so now I just have to draw my slope field. What number is this? Ooh, I didn't write the year down. Oh boy. Hopefully I got these right. I was going to double check, but I got this. So at 1 comma 2, the slope is 0. So I do a 0 slope. At 1, 1, the slope's 1. So I draw a line with the 45 degree. That's pretty darn good. And down here, the slope's 3. How do I draw a slope at 3? I just have to make it really steep. Steeper than that. Then at 0, negative 1, I got a 1. So I can do a slope of 1. Make sure your rise and your run are pretty close. Then at 0, 1, I got negative 1. So here I do a slope of negative 1. And at 0, 2, I have a slope of negative 2. I just have to make it steeper than the negative 1, but not as steep as that. So we're looking pretty good here, I think. I don't know for sure because I don't know what year this is. That's part A. I drew the slope field for the given situation. All right, now I am going to do part B. Find the second derivative. Determine concavity in quadrant 2. Give a reason for your answer. That's kind of fun. It's actually kind of fun. This is the question that's going to kind of throw people off because it's kind of a different question. All right, so, okay, let's just do this. Let's find the second derivative. This is part B. dy dx is 2x minus y. Now, when you're doing this, y is your function, so this is box. So if I take the derivative of the left side, I get the second derivative. The derivative of 2x is 2, but the derivative of y is dy dx. Now, I need to replace dy dx with what it is. So I'm going to get 2 minus, and dy dx is 2x minus y. So I'm going to get 2 minus 2x plus y. There is my second derivative. Now it's asking me, what's it asking me? The concavity in quadrant 2. What's true in quadrant 2? In quad 2, x is negative and y is positive, right? If x is negative, a negative times a negative is positive, and y is positive, it's positive. So that's going to be my answer. The second derivative, is positive in quadrant 2 because x is negative and y is positive. Bam. Okay? So that's the analysis. Now, I think we're done with part B. Okay, I'm going to move on to part C. I'm kind of stalling because I'm trying to find the FRQ that matches up with this so I can check my answers so I don't lead you astray. So I'm slightly stalling here. Oh, I found it. Okay. So I think we're looking good. So part C. Let me check my slope field, see if it matches theirs. Yeah, looks pretty good to me. Okay, part C. Let f of x be the particular solution to the differential equation with initial condition f of 2 is 3. Okay, let f of x be the particular solution. They don't ask you for the particular solution. Be very careful. Read carefully. A lot of students found the particular solution. It's not saying find it. It's just saying f of x is the particular solution. Okay? Does f have a relative max or minimum or neither at 2? Now this is going to throw some of you off because you're going to forget there's two tests for relative min or relative max. One is the first derivative test, and the first derivative test, and here's where it gets crazy. In the first derivative test, you plug in points left and right of your point, right? So you're going to say, okay, my point's 2, 3. What's to the left of 2, 3? But here's the problem. Your derivative contains x and y. If you're doing a point to the left, okay, so for x, I can plug in, what, 1.9? But what do I do with the y? That doesn't make sense to me. So the first derivative test becomes a problematic in this situation where you have a y in your derivative. So remember the second derivative test. Okay, I'll explain the second derivative test. First, you need to find dy dx at the point they want you to test, 2, 3. That must be 0 or your second derivative test isn't going to work. So that's going to be, am I doing this right? I guess I am. At 2, 3, I'm going to have 2 times 2 minus 3 equals 1. Okay, so the slope at 2, 3 doesn't even, it's 1. It's not a critical point. Therefore, I have neither a relative max or neither relative min. So I would say because dy dx at xy equals 2, 3 does not equal 0, therefore there is neither a rel max or rel min. Okay, that's part C. Part D. Okay. Find the values of constant m and b where y equals mx plus b is a solution to the differential equation. Okay, this one was like a shock to the system for a lot of people. It's a tough question if you don't have practice, but once I explain it, it should make a lot of sense. Here's our differential equation. dy dx equals 2x minus y. Okay? Now, they're telling you y equals mx plus b is a solution. If y equals mx plus b is a solution, that means if I stick it in here and I stick it in here, it must work. It must be true. Okay? So that's what I'm going to do. I'm going to put y equals mx plus b into both of those. According to problem part D, it tells you that mx plus b is a solution, so I'm going to plug it in to my differential equation, right? And let me make sure I'm doing the right differential equation. Yeah, to the differential equation. So the derivative of the left side is just m. And on the right side, I get 2x minus mx plus b. That must be a true statement. So I'm going to do more stuff. I'm going to factor out the x. And we get 2 minus m plus b. Okay, are you ready for this? In order for this side to equal this side, a couple things must happen. What's the value of x on this side? Okay, I have 2 minus mx. What's x over there? And you're going to say, I don't know. Okay, there is no x. So there's 0 x's over here. They don't write down 0x when you don't have x's. So this must equal this. All right, that must equal that. I'll circle that. That must equal that. So I can make this statement 0x equals x times 2 minus m. 0 equals 2 minus m. M equals 2. Crazy. Okay? And then the parts without the x must equal. M must equal b. So m must equal b. But what's m? M is 2. So b is 2. Okay? I think I have a sign error somewhere here. I do. I'm supposed to distribute that minus. That should be minus b. Me apologies. Minus b. But m, whoa, what just happened? Whoa, 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 whoa. But m is 2. Plug a 2 here. B comes out to be negative 2. Okay, so that's your m and b. That's the end of the problem. That was kind of a crazy, part D was kind of crazy. But again, part D was worth 3 points, but most people are going to get that wrong. The ones that get 4s and 5s in the AP test will get part D. Those who get the 3s will get A, B, and C for the most part, or most of A, B, and C. But that's the end of this video. Bye-bye.